When a liquid is in contact with a surface maintained at a temperature above the saturation temperature of the liquid, boiling will eventually occur at that liquid-solid interface. Based on the relative bulk motion of the liquid to the heating surface, the boiling is divided into two categories: pool boiling and convective boiling. Pool boiling is the process in which the heating surface is submerged in a bulk of stagnant liquid. Pool boiling curve. It is a plot of heat flux versus excess temperature. Excess temperature is the difference between T surface and T saturated of liquid. There are four regimes of pool boiling curve: natural convection boiling, nucleate boiling, film boiling. A typical boiling curve of saturated water at atmospheric pressure is as shown in figure. In natural convection boiling regime, where the delta T excess is less than 5 degrees Celsius, heat transfer from heating surface to liquid is by natural convection only. When excess temperature increases beyond 5 degrees Celsius, the nucleate boiling regime starts at point A. The first bubbles start forming at point A of the boiling curve at various preferential sites on the heating surface. The bubbles form at an increasing rate at an increasing number of nucleation sites as we move along the boiling curve toward point C. The nucleate boiling regime can be separated into two distinct regions. In region A to B, isolated bubbles are formed at various preferential nucleation sites on the heated surface. But these bubbles are dissipated in the liquid shortly after they separate from the surface. In region B to C, the heater temperature is further increased, and bubbles form at such great rates at such a large number of nucleation sites that they form continuous columns of vapor in the liquid. These bubbles move all the way up to the free surface, where they break up and release their vapor content. The large heat fluxes obtainable in this region are caused by the combined effect of liquid entrainment and evaporation. At large values of delta T excess, the rate of evaporation at the heater surface reaches such high values that a large fraction of the heater surface is covered by bubbles, making it difficult for the liquid to reach the heater surface and wet it. Consequently, the heat flux increases at a lower rate with increasing delta T excess, and reaches a maximum at point C. The heat flux at this point is called the critical or maximum heat flux, Qmax. Nucleate boiling is the most desirable boiling regime in practice because high heat transfer rates can be achieved in this regime with relatively small values of delta T excess. Transition boiling. As the heater temperature and thus delta T excess is increased past point C, the heat flux decreases. This is because a large fraction of the heater surface is covered by a vapor film, which acts as an insulation due to the low thermal conductivity of the vapor relative to that of the liquid. In the transition boiling regime, both nucleate and film boiling partially occur. Nucleate boiling at point C is completely replaced by film boiling at point D. In film boiling region, the heater surface is completely covered by a continuous stable vapor film. Point D, where the heat flux reaches a minimum, is called the Leidenfrost point. The presence of a vapor film between the heater surface and the liquid is responsible for the low heat transfer rates in the film boiling region. The heat transfer rate increases with increasing excess temperature as a result of heat transfer from the heated surface to the liquid through the vapor film by radiation, which becomes significant at high temperatures.